The test for Calculus AB today concluded, and I was really impressed that so many of you attempted the bonus questions on the back. Obviously, there was a lot more success on the first bonus problem than the second bonus problem. Makes sense. The first bonus problem was sort of a wrinkle and an extension of something that we've done before. The second bonus problem was really tough. Having said that, there was a lot of talk about it, a bunch of people telling me it was the hardest thing they'd ever seen, and a bunch of people just kind of curious about how to do it. Only 2 students got it correct. Technically, only 1 got it fully correct. Only one of you got it fully correct because the other person had some decimal integrity issues with rounding the value of k. But in any event, I wanted to demonstrate this, and especially since I haven't done many YouTube videos in a while, I think these kinds of problems are always somewhat engaging. So the problem in question is on the page right here, with no work, of course, associated with it. And this problem is basically as close as I could get to a one-stop shop of using all the techniques from this unit that we just covered, save for LRAM, RRAM, trapezoids, and midpoint Riemann sums. So that's the only thing that didn't make it in here. At its heart, this problem asks you to convert a Riemann sum into a definite integral. So there's sort of the first task. It then asks you to use U substitution to simplify or transform that integral into a different form. It asks you to use the fundamental theorem of calculus to set up a relationship between some variables. It asks you to use a graphing calculator to solve a relationship for a particular value, in this case k. Then it asks you to do sort of the same thing again, but also demonstrate the integral properties and being comfortable using the integral properties, including a particular one that's sort of intellectually difficult to navigate. And then finally, the 6th thing that I'll throw out there that isn't truly a pure calculus thing, but that I think makes this problem in particular pretty difficult and sort of novel for the ones that I tend to write, is that this problem doesn't progress purely linearly, which means it isn't a problem where you just start at the beginning and then you slowly progress and get to the answer. You progress forward, you reach a point, I'll call it a point of inflection, and then you have to stop, turn around, and then do something else in order to kind of bridge your answer back. So as you can expect here, I am going to solve this problem. If you want to think about it a little bit longer, you can pause the video right here, but I'm going to proceed forward. Actually, you could pause the video at any point before this point. They're all there. So in our case, the first thing I'm going to attack is this Riemann sum. So I mentioned that there's this big old Riemann sum, so that's where I want to start. What is that thing going to turn into as a definite integral? Well, there's a couple different things to hit. First of all, because we've got that plus 1 on the inside, my definite integral is going to begin at 1. And because the width is 8 over n, our second endpoint is going to be 8 units away, which is 9. That way there's a separation of 8 between them. On the inside then, the 8 over n will become our dx. That's perfectly fine. And if you recall, when we have wi plus a, that kind of allows us to find like the partition values that break up each of our places, or the places where we're going to calculate the heights of our rectangles. That's always equal to x. So I'm going to effectively replace each of those with an x. And yeah, the one in the denominator will get replaced as well. And we'll be left with f of the square root of x divided by the square root of x, and of course dx for the width. So there's our integral. Now this doesn't help us at all, and we can't anti-differentiate it because it's f. We don't know anything about f, really. But what we can do is we can perform U substitution. I'm not even sure if I listed that as a thing that you have to do. I think I did. But in any event, we'll perform U sub. I'm going to let u equal the square root of x. If that's true, then du will be 1 over 2 square root of x, and of course dx. And if I proceed that forward just to kind of make the adjustment, we could say that dx is equal to 2 root x du. And that 2 actually threw a lot of people off. I saw a lot of good work on this problem that just didn't, end up fruitful and end up in the correct answer. But that 2 in here actually threw a bunch of people off, interestingly enough. Now, in addition to that, this is a definite integral, so I am going to definitely change the limits of integration as well. We have x equals 9. But if x is 9, u is going to be the square root of 9, also known as 3. And likewise, if x is 1, u is going to be the square root of 1, which is equal to 1. So the lower limit of integration actually won't change in this new system. Having said that, our integral up there is going to be transformed into the integral from 1 to 3 of, we had f of u. And then it's tempting to immediately go over u, but let's hold back for a second. This will be square root of x down there, and then dx will be replaced by 2 root x dx. Or sorry, du. Apologies. That's helpful because you might notice the root x's are going to divide out, and we can write this entire integral as 2 times the integral from 1 to 3 of f of u du. So there's our integral transformed. But having said that, it's kind of like, once again, we reach this point where your question is, well, what do we do with that? Well, it says in the problem that Riemann sum, which is our definite integral is equal to 16. So this whole integral is equal to 16, which means, and I'm going to make this change now, I think this is one of those things that kind of threw people off, I can divide both sides by 2 here, and I'm going to get the integral from 1 to 3, of f of u du is equal to 8. That is sort of our first checkpoint place. That wasn't something that I gave a point for, or I was going to give a point for. I was looking for the value of k, but that's a huge starting point. We need this piece of information to proceed forward, and if you look at your work and you're like, I did all that, see if you accidentally left this as 16. By the way, there were different versions across all 4 classes. This version, you got 8. Obviously, the other ones are all parallel. They behave in the same way, more or less. So here's what we got. We have this information. So now it's like, well, what else do we have? What else is there to do? Well, the next thing it says is that h prime of x is equal to f of x. So in other words, I'm going to take this relationship we just arrived at, and I'm going to try to rewrite that. So we know the integral from 1 to 3 of f of u du is equal to 8. But f of u is just h prime, so that means the integral from 1 to 3 of h prime of u du also equals 8. But here's the thing. The integral from 1 to 3 of h prime of u du is equal to h of 3 minus h of 1. That is the fundamental theorem of calculus. And that wouldn't normally get us anywhere because we don't know any more about h than we really do f, except the problem gives us some information about h of 3 and h of 1. Notice again, you're kind of filling in the pieces. It's like, oh shoot, I need to know this. Well, it's given to you in the problem. I wrote an efficient problem. So in here, based on that, what we now have is that this integral, which we just said was equal to 8, right here, it's equal to 8. 8 is equal to k cubed minus 3 minus cosine of k. And in this case, there is no way for us to solve this by hand. It's not just hard, it's just not something we have the ability to solve by hand. So to evaluate this, I am going to turn to my friendly neighborhood graphing calculator. And I'm going to see where the intersection happens. So let's do that really fast. I didn't preset it all up, but I did have my calculator handy. So let's go in here. So I'm going to graph, first of all, not 100 and 200. I'm going to graph y equals 8 for our first function. We want to find the intersection here. And then I'll let x play the role of k. So we'll have x cubed minus 3. Let's make sure that did it okay. There we go. Minus cosine of x. And then I'm going to zoom 6 this. I'm going to hope that it shows up. There it does. We've got one intersection point, so let's go find the intersection point. Second calc, I'll choose option 5 for the intersect. Enter, enter, why don't you? And it's going to give us that x is equal to 2.1844 something. So 2.1844 something. So k is equal to 2.184. I think it was 7. I just want to get a couple decimals in there. Integrity does matter here. 447. And then I'm going to put this, ... So as I mentioned earlier, there was a point that I would have awarded you. I think it was 2 points out of the 5. That would have been the first sort of benchmark point, if you could get there. So with that said, I'm going to pause for a second and move this to the next page, and then we'll continue the problem. Okay, here are our results from the previous page. The integral from 1 to 3 of f of u du is 8. We found that using u substitution after converting our Riemann sum. And second, after applying the fundamental theorem of calculus, or alternate fundamental theorem of calculus, and the given information about h of 3 and h of 1, we found the value of k. Now all that remains for us to do in order to finish this problem is to evaluate this integral. And the first thing I'm going to do is I'm going to split it right there. Like, this is begging for that mistake that I've talked about many times. So I'm going to split this into 2 integrals. This will be the integral from 0 to the natural log of 3 of 3 e to the x, f of e to the x. And by the way, as soon as you see that, hopefully your mind starts to send off an alarm bell that goes, substitution. That looks like substitution. It will be. And then second, I'll switch to orange here. It'll be the integral from 0 to the natural log of 3 of just plain old k dx. So that's what we got. So each of these is going to be evaluated a little bit differently, but I'm going to start with the one over here. So that e to the x on the inside screams for me to use u substitution, so I'm going to. U will be e to the x. The derivative of u will then be e to the x dx. And of course, du over e to the x will equal dx. Simplifying these pieces, or actually before I even simplify, let's just convert the limits of integration for simplicity. If x equals the natural log of 3, then that means u is going to be e to the ln of 3, which, I mean, you had a calculator, so if you didn't know what this was, you could find it, but that means u is equal to 3, because e and ln are inverses. And if x equals 0, then u will be equal to e to the 0, which is 1. So given all that information, we can actually transform this expression, at least the first part, into, and actually I'll do it down here before I write it there, we'll get the integral from 1 to 3 of 3 e to the x, f of u, and then times du over e to the x. And as you might expect, the e to the x is e to the exit, and we are left with 3 times the integral from 1 to 3 of f of u du. Now, if you're getting a little bit of deja vu, that's honestly good, because this is a familiar thing. In fact, it's written in pink just a few lines up above where I'm working right now. We know the value of the integral from 1 to 3 of f of u du. It's equal to 8. So we'll take advantage of that in just a second. The other piece, though, that we have here is this orange integral. And we know the value of k, that 2.184 thing that we'll be careful with in just a second. But the important thing is k is just a constant, and the integral of a constant is just a line with that slope. So for the second part, we're going to evaluate kx from 0 to the natural log of 3. And with all this in place, we can start to make our substitutions and evaluate this. This will be 3 times that integral's value, and as we said before, that integral is equal to 8. So we're going to get 24 for that first portion. And for that second part, we're going to get k times the ln of 3 minus k times 0. So after all of this stuff, if we were to kind of write out what this expression is going to be equal to, I'll write it in my favorite purple. This will be 24 plus 2.18447, etc., times the natural log of 3. And from here, all it matters is we just need our calculator to kind of tell us what our value is going to be. So I'm going to do something here really fast just to kind of emphasize it. It's not a big deal, but I'm going to save that exact value. I'm going to let x be stored as alpha k. And there it is. And now I'm going to do 24 plus k. I don't have my glasses on, so I got to make sure I do this right. Times the natural log of 3. That's going to give us, it is 26.399. So we could write that as 26.400 or 26.399. So there is the answer to that second bonus question. This was the, again, as I mentioned earlier, this was the second period version. The other ones all got modified a little bit, but the process would be exactly the same. And if you want to check your specific answer with me, you can, although you can walk it through at this point and get there. So, like I said, this was just kind of a creation I came up with last week, trying to come up with something that involved a bunch of the techniques of the chapter. I think that makes for a good bonus question. It really makes you earn it. So congratulations to the 2 students who got it fully correct, that did everything correctly in here. And if you didn't, hopefully you learned a little bit of something from it. But regardless, thanks for working on it, and thanks for being interested. So I'm calling it a night, and I'm going to go, no, I was going to say I'm going to go sleep, but that's not true. I'm going to go write makeup tests. Bye.